Hello, Nick Lafker here, and welcome again to Operations Management. I mentioned before about how if we have things like trends, like seasonality, well, how do we deal with them? Well, with trends, the best thing to use is what's known as a trend line. And a trend line is, well, for lack of any better way to put it, it's pretty much what it says. It is a line that reflects a trend in a set of data. Now, the trend lines allow for several things. One, it allows for a long-term forecast. So you could, in theory, use a trend line to forecast for many years from now. That said, do remember that the further out you go, the less accurate it's likely to be. That said, what a trend line is it is a line. You use a linear regression model to find the line that best explains the relationship between a set of data and the results. So, you find a relationship between the forecasted value and, in this case, time. So, with any trend line, you have a set of data, x and y values. Usually, the x value is time and y is whatever you're trying to forecast. And so you find the line that best describes that data. Now, fortunately, this is what Excel is for. So in general, what you have is you have a set of data that can be described as y equals a plus b times x, which is your typical formula for a line, plus some sort of error. And the error is simply the difference between that forecast and the actual results we get. So what a trend line does is it tries to minimize the sum of the square of those errors. So this is generally viewed as the best descriptor of the data that we have. So you take a bunch of data and you come up with a line that describes what's happening with that data, that describes the relationship between the x and y values for that data. Now, to make a trend line in Excel, well, the first thing you have to do is you have to construct an XY scatter diagram. So you put your x and y values, y being the thing you're trying to forecast, like sales, like demand, and x in this case usually being time. And you construct an XY scatter diagram for that data. Once you have that, well, you can do one of two things. You can select chart and then add trend line, or you can right-click on the data series. When you right-click, the option to add a trend line shows up, and usually in cases like this, there are options that are available, such as showing the formula, such as showing the r squared value, and we'll talk about r squared over the course of this lecture. So, a trend line, it provides a formula. Y equals a plus b times x. X, like I said, this is the independent variable. This is what we intend to use to forecast. And y is the dependent variable. This is what we're trying to forecast. So y is what we're trying to forecast, x is what we're trying to use to create that forecast. And a and b are simply, well, a is simply the y-intercept, as it's known, and b is the slope. So going back to your math, that's what a formula for a line is. So what we do is we insert some sort of value for x. Like I said, usually if it's a time series, x is time. And we see what the result for y is. So with the previous page's example that we had, well, y is equal to 23.27 plus 1.08 times x. So if we have x equals 30, in other words, where time equals 30, what forecast do we get? Well, we put 30 into our formula, and we solve for y. So in this case, y is equal to 23.27 plus 1.08 times 30. Well, that equals 55.63. Now, when it comes to regression methods, and a trend line is simply the simplest form of regression, you'll have several things that can tell you how you're doing with regard to this regression. One of these is called correlation. And what correlation represents is it shows how strong the relationship is between these two variables, between y, what we're trying to forecast, and x, which is what we're using to make the forecast, which is usually in this case time. So we use correlation coefficient as a measurement of that. The values for correlation range from -1 to 1, and it measures the degree to which y is related to x. We use it to understand the relationship between these two variables, x, time, what we're using to create the forecast, and y, demand, what we are trying to forecast. Now, these graphs represent what kinds of correlation we would get given a set of data. If there is a perfect relationship, a perfect positive relationship between y and x, in other words, the larger x is, the larger y is, and it's a perfect straight line relationship, well, that means that our correlation coefficient, our r, is equal to 1. That said, we're not likely to get this. Usually what we get is something that looks kind of like that second graph, the one that has r equals 0.93. There's clearly a relationship between x and y, the time and demand, for instance. But it's not a perfect relationship. And so our correlation coefficient is high, in this case 0.93, but it's not 1. That's still good. That's still what we want. Sometimes there may be a negative relationship between x and y. In other words, as time increases, that demand decreases. Well, if there's a negative relationship between y and x, that means that our correlation coefficient is going to be negative. That's just fine. That happens. So if it's a perfect negative relationship, that would mean that we'd have a correlation coefficient of -1. Now, what we don't want is what's in that last graph there, the one that has r equals -0.05. If r is close to 0, it means that there isn't much of a relationship between our x and our y. There isn't much of a relationship between time and demand, for instance. So there isn't a relationship between what we're trying to forecast and what we're using to forecast. So in that case, that tells us that our forecasting model isn't very good, that it isn't that useful. So we want a correlation coefficient. We want an r somewhere either close to 1 or close to -1. A correlation coefficient close to 0 really doesn't help us all that much. So that tells us what we can use if we have a trend in our data, if we have an increase or decrease over time. So what do we do about seasonality? Well, we have several options available for seasonality. We have seasonal indices, and the idea of seasonal indices is that we simply adjust our trend line such that if it is a particular month or it is a particular season, we multiply it based on that season. So if our average sales in November are 1.2 times our average, well, why not just multiply our forecast by 1.2? So in this way, we generate multiples. Sometimes we can use additive seasonal indices, but in general, multiplicative seasonal indices generally work best. So what we do is we take a trend line, such as what we just came up with, and we multiply it by the seasonal index for that time period. And the other option is what's known as a multiple linear regression. So what happens with multiple linear regression is it's a regression. It's a really fancy trend line. It's just that instead of having a single x and multiple y values, we have one y, what we're trying to forecast, but we have multiple x values, and that's what we're going to talk about next. By the way, I suggest you look at the videos with regard to the SGFC football case and the corresponding Excel spreadsheet that goes along with it. In cases like that, I show how to generate seasonal indices And I also go over how to use multiple linear regression to come up with a time series forecast with seasonality. Now, I mentioned multiple linear regression, and it's a beautiful tool because the idea is simply this. With a trend line, we had an x value and a y value. Well, why not use more than one x value in our model? In other words, instead of having just a single x and a single y, why not have more than one x and y? So we have multiple independent variables, such as stock price or advertising, that can be used to forecast for a dependent variable, what we're trying to figure out. So, for instance, in this example here, we have sales that are predicted by advertising expenditures and price. So, how would we see this happening? Well, in general, we would expect that the greater we spend on advertising, the greater our sales would be. And we also expect that the higher the price of the item, the less the sales will be. So we can expect both of these, both advertising and price, to have an effect on our sales. Now, multiple linear regression can be used for two different types of forecasting. The first is what's known as associative forecasting. With associative forecasting, we get to the heart of the matter. We get to what is causing our results. As we saw before with sales being dependent on advertising and price. So we take a set of independent variables that we expect will have some effect on what we're trying to forecast. And we compare these variables to our final result, what we're actually trying to forecast, whether it be sales, whether it be demand, whether it be the temperature. And from this, we find a formula that explains the change in that final result, in sales, in demand, as a result of changes in these independent variables. And then there's what we call time series forecast with seasonality. The idea here is that we include variables for including time, so we have that trend portion of it. And then we have what are known as dummy variables. And dummy variables are simply variables that can have one of two values, 0 and 1. If it is that season, if that case is true, for instance, then this dummy variable has a value of 1. If it is not that season, if it is not true for this particular variable, then it has a value of 0. And by doing this, you can have a, if you will, a yes-no case with regard to forecasting. Is it January? Yes, then the value of the variable for January equals 1. If no, then it equals 0. So we can forecast using seasonality by having each season, well, almost each season, and I'll explain why in that other video. Almost each season has a variable corresponding to it. Now, as for what makes a good regression, what makes a good multiple linear regression, what makes a good trend line, well, we generally look for two things. One is what's known as a high R-squared value. Now, I mentioned before the correlation coefficient and that it measures this relationship between x and y. Well, what an R-squared value does is it's the square of that correlation coefficient. Now, the R-squared is the percentage of the variability in y that is explained by the independent variables x. So whatever we use in our formula, the R-squared represents the percentage of the variability in what we're trying to forecast that is actually explained by those variables. So if we have an R-squared of 0.75, then that means that 75% of the variability in what we're trying to forecast is actually explained by the model. Now, R-squared is dimensionless, so this is one of those things that I'll be talking about a lot in this course, and that is that numbers are almost never just numbers. Well, R-squared is one of the few numbers that is just a number. It has no dimensionality to it. So R-squared is just between 0 and 1. We want it to be as close to 1 as possible. Now, the other thing that makes a good regression is a low value for what's known as the standard error of the residual, or the standard error. Now, standard error is a measure of the difference between our estimated values and the actual observed values. So, how close are the actual values that we have to our estimates based on our forecasting model? Now, the standard error, it has, well, I'm about to say something that would offend a statistician. A standard error is, for all intents and purposes, a standard deviation. Now, a statistician would take offense at that statement, but we can use it in much the same way as we would normally use a standard deviation. So, in the same way as a standard deviation, whatever our units are for what we're trying to forecast, that'll be the same units that we have for the standard error. So if we're forecasting for, say, the dollar value of sales, so dollars, well, that means that our the dimensionality for our standard error would also be in dollars. Now, I go into how to develop a multiple linear regression model in some of the other videos that I've included. In particular, the St. John Fisher College football case videos that I've included. That said, how we do this? Well, first thing we do, in general, is we need to install the data analysis add-in package into Excel. And I've included some instructions here. So, first thing we do, we click on the MS Office button in the upper left-hand corner and click on Excel Options. Now, once this pop-up comes up, then you'll install the data analysis add-in package by selecting add-ins from the menu. And then near the bottom, you'll see this drop-down selection box called Manage. Well, see that Excel add-ins is the option selected in the box. You click on Go, and that takes you to the various add-ins that you can add into Excel. So, once the options with regard to add-ins once that comes up, you select the data analysis add-in package and put that in Excel, select the analysis toolpack and click OK. After this, the data analysis toolpack should be available. So once the analysis toolpack is installed, well, then you can select the Excel regression tool by finding under the Excel menu, Data, Data Analysis. So you select on Data Analysis, and this brings up a whole bunch of different options. You select Regression under Data Analysis to bring up the regression tool. Now, there's several options available when you are completing an Excel regression. First, you have to input the Y range. In other words, you have to put in the Y values. So, what are you trying to forecast? You need some ideas to what's happened in the past, so you need some results from the past to put in. So your Y range, this is what you're trying to forecast. This is sales. This is demand. And then there's all of the X variables. So these are all of the things that you intend to use to forecast, to develop the forecast. So this might be things like time. This might be things like advertising expenditures. This might be things like price. And these you put in your model. It's generally a good idea to use labels when developing an Excel regression tool. So use labels for the data. And there's some other options that are available, such as might be a good idea to select residuals. One that I would not recommend is that one possible option is that you have what's known as the y-intercept being 0. Don't select this. This is not a good option to have generally. So once everything's ready, once your Y range is selected, once your X range is selected, you've selected labels so that you can create some sense from the resulting report. At this point, you hit OK, and you see the results. Now, what you will get for your results will look something like this. This is what's known as an ANOVA report, A-N-O-V-A. Now, an ANOVA report has some information, some useful information. For instance, you have the correlation coefficient R under multiple R. You have, of course, the R squared. That's fairly straightforward. What the adjusted R squared deals with is it takes that R squared and adjusts it for the number of variables you're using in the model. In general, we prefer simpler models, and there's a very good reason why. The more complex a model we have, the more that model ends up trying to forecast for random variation. And forecasting for random variation does not work. Forecasting for random variation is generally a bad thing. The result is that the more complex a model gets after a certain point, the less accurate it becomes. The less accurate it becomes for forecasting for future results. And I know that may sound counterintuitive, but if you consider this idea of random variation, and that there are some things that cannot be forecast, if you have a model that tries to forecast them, it's actually going to be less accurate in the long run. So, we generally want a simpler model, and I do talk about this in a little more detail in the St. John Fisher College football case videos that are attached. So, I suggest watching those to get some more details with regard to how to develop and use an Excel regression output. We also have the standard error of the residual. But the important parts of the ANOVA report are the coefficients and the p-values. The coefficients, this is our model. This creates our model. This shows our model. So in this case, our y-intercept is at 12,000. So our if we have y equals a plus b times x, that 12,200, that would be our a. That would be our y-intercept. And in this case, education, and this I think was an estimate of a person's earnings, annual earnings, based on their education level. And so we have $1,800 as our b, as our coefficient. So our model would be 12,200 plus 1,800 times education. So that's how this works. In other words, the coefficients, these form our model. Now the p-values, what this tells us is these coefficients are estimates of what these actual values are. It's not perfect, it's not completely exact, but it is close. That said, there's always the possibility that these coefficients in real life are actually zero. So what the p-value is if the number is zero in real life, what's the probability that you could get these numbers in a regression model? And we use these p-values as a guide as to which variables we should eliminate from the model to simplify it and to hopefully make it easier to use and easier to understand. Now, before I start, I do recommend that you watch the video with regard to the St. John Fisher College football case, where I go over how to formulate and develop a regression model and the various steps that are involved with that. That said, there are a few more things I want you to know about regression models. First, with a regression model, perform a reality check. Do the numbers make sense? Sometimes the numbers don't make sense at all. It doesn't seem to make any sense whatsoever. If not, find out why not. For example, you would expect that there to be a positive relationship between advertising expenditures and sales, right? The more you spend on advertising, hopefully the greater your sales are going to be. So if there's a negative relationship, well, it might be a good idea to look at the data and see what's going on. One of the causes of, shall we say, odd data is what's known as collinearity. Now, the way collinearity works is this. You have two variables in the model that are themselves related, that in some ways are measuring the same thing. For instance, imagine both height and weight in a regression model. Well, height and weight are also related to each other. After all, the taller a person is, the heavier that person is likely to be. So if you have a model where both height and weight are part of the model, they kind of interfere with each other in terms of developing the model. So what sometimes happens is with both height and weight, we're measuring the same thing. We're measuring the size of a person. So what can happen is by eliminating one of these, say eliminating height, all of a sudden the other variable, weight, makes more sense. Now, one last thing is that just because two variables aren't related linearly doesn't mean they aren't related. In other words, sometimes the x and y variables may be related, but they may not be related linearly. Advertising is actually a good example of that. The more we spend on advertising, we expect an increase in sales, but we expect that to increase at a much slower rate the more we spend. So if it's not a linear relationship between y and x, why not transform the independent variable somehow? In other words, instead of using x, use x squared or use the natural log of x. Sometimes by transforming that independent variable, that x variable, we can find a model that makes far more sense. Now, I do recommend again that you look over the videos with regard to the St. John Fisher College football case, where I go over how to generate a multiple linear regression model. I also go over how to generate seasonal indices. And for the next video, what I'm going to do is I'm going to talk about how to measure a forecast to see how well it's doing. In other words, how do we measure forecast error? Thank you.